Hello friends, welcome to my YouTube channel. Today we will learn about op-amp as differentiator. The topics covered in this video are how op-amp can be used as differentiator, differentiator input and output waveforms, limitations of simple differentiator circuit, frequency response of simple differentiator, practical differentiator circuit, frequency response of practical differentiator, and finally we will solve some examples on differentiator circuits. We have already discussed about op-amp as an integrator in my earlier video. An op-amp differentiator circuit configuration is inverse of the integrator circuit. Here the position of capacitor and resistor have been reversed if we compare with the integrator circuit. Now the capacitor connected to the input terminal of the inverting amplifier, while the resistor provides negative feedback to the op-amp. The output of an integrator is proportional to the area of the input waveform over a period of time. A differentiator circuit produces an output voltage that is proportional to the rate of change of input signal. Note that these two operations are opposite. Suppose if we apply a fixed input signal or DC signal to the differentiator circuit, then the output will be equal to 0 volt because the input signal is not at all changing with the time. If the input of the differentiator is square wave, the output of the differentiator circuit have positive and negative spikes where the input waveform transitions are happening. So in this way, differentiator circuit can be used to find the high frequency components of input signal, or we can say for the edge detection purpose. So now let us analyze the circuit to understand how this circuit acts as a differentiator. Since the point A is at virtual ground and due to infinite input impedance of the op-amp, all the input currents that flows through the input capacitor entirely flows through the feedback resistor RF. So by applying KCL, we can say that input current IC equal to feedback current IF. Here the voltage across capacitor VC equal to Vin minus 0, that equals to Vin, and voltage across feedback resistor VR equals to 0 minus Vout, that equals to minus Vout. We can write this capacitor current IC as C dVc by dt. Here Vc can be written as Vin. So our expression becomes C multiplied by dVin by dt. Here feedback current IF can be written as minus Vout divided by RF. Because of input current IC equal to feedback current IF, these two expressions are equal. That is C dVin by dt equals to minus Vout by RF. So we can write Vout as minus RF multiplied by C dVin by dt. This equation shows that output is the differentiation of the input signal with an inversion and scale multiplier R into C. If we examine this equation, we can say that if the input voltage is constant, that is dVn by dt equals to 0, then the output voltage is also 0. The faster the input voltage changes, the larger the magnitude of the output voltage. Let us now see the output waveforms for different input signals. When a fixed DC level with an amplitude of 3 volt is applied to this differentiator circuit, the output voltage is 0 volts because dVin by dt equals to 0. But practically the output is not 0. Since the input step wave takes some time to rise from 0 to 3 volt, hence the output voltage appears like this. If the input of the differentiator circuit is changed to a square wave, the output of differentiator has a positive and negative spikes where the input waveform transitions are happening. Because of the inverting action of the op-amp circuit, the positive rising edge of the input signal causes negative spike at the output, and the negative or falling edge of the input signal causes positive spike at the output, corresponding to the charging and discharging of the input capacitors. For a sine wave input, which is mathematically represented as Vt equals to Vm sin omega t, where Vm is the amplitude of the input signal and t is the time period, then the output of differentiator is given as Vout equals to minus Rf multiplied by C dVm sin omega t divided by dt. that equals to minus Rf multiplied by C Vm cos omega t. Thus the output of a differentiator circuit is a cosine wave, hence it is 90 degrees out of phase with the input signal. If we apply a triangular wave input signal to the differentiator circuit, the negative slope or falling level of the input signal produces a positive voltage at the output, and a positive slope or rising edge of the input signal produces a negative voltage at the output. So in this way, rising and falling slopes of triangular wave input will produce a square wave at the output of a differentiator circuit. The amplitude of the output signals depends upon the values of feedback resistor and input capacitor. Now let's observe limitations of simple differentiator circuit. Input signals are applied through the capacitor. So the capacitive reactance is the most important factor in the analysis of the differentiator circuit. Capacitive reactance Xc can be expressed as 1 upon 2 pi Fc. Capacitive reactance Xc is inversely proportional to the frequency. So we can write inverting op amp Vout as minus Rf divided by Xc multiplied by Vin. Here the gain of the circuit equals to minus Rf by Xc. This can be expressed as minus Rf multiplied by 2 pi Fc. Therefore, from this expression, we can say that the gain of the differentiator circuit directly proportional to the input signal frequency. So, if the input signal frequency increases, the gain of the differentiator will also increases. If you observe the frequency response of the simple differentiator, it will look like this. The gain of the differentiator circuit directly depends upon the frequency of the input signal. Hence, for the DC inputs where the frequency is 0, the output is also 0. As the frequency of the input signal increases, the gain of the differentiator will increase at a rate of 20 dB per decade. And at one particular frequency, the gain of the differentiator becomes 0 dB. That frequency is known as 0 dB frequency or F0. If the input frequency is less than F0, the gain is also less than unity. F0 can be expressed as 1 upon 2 pi multiplied by Rf into C. But here the gain of this differentiator will be restricted by the open loop gain of the op amp. So the maximum gain which we can achieve from the differentiator circuit will be the intersection point of the gain of the differentiator and open loop gain of the op amp. So the frequency response of the simple differentiator looks like this. The differentiator circuit produces high gain at high frequencies. So we can say that differentiator circuit is very sensitive to high frequency noise. That is, suppose if our input signal frequency is of low frequency and if there is a high frequency noise in the circuit, then when amplified, the noise will dominate the input signal. Apart from that, when operating at high frequencies, the differentiator circuit becomes unstable and starts to oscillate. The input impedance of the differentiator circuit will be equal to the reactance of this input capacitor. Zin equal to Xc. Capacitive reactance Xc equal to 1 upon 2 pi Fc. As the input signal frequency increases, the capacitive reactance reduces. So the input impedance will also reduces at high frequency applications. So the two limitations are differentiator circuit is very sensitive to high frequency noise, and if input frequency increases, the input impedance will reduces. So in order to overcome the limitations of simple differentiator circuit, an extra input resistor R is added in series with the capacitor, so that we can avoid high frequency sensitivity and low input impedance limitations of simple differentiator circuit. Now the input impedance of this practical differentiator not only depends on the reactance of the input capacitor, but also depends on the input resistor value. So we can say that input impedance Zin equal to square root of R square plus Xc square. As the input frequency increases, the capacitive reactance Xc will reduces, and because the input resistor R, the input impedance Zin is always greater than the value of resistor R. So in this way we can overcome the low input impedance limitation. And apart from that, as the input signal frequency increases, this capacitor acts like a short circuit and the gain becomes the ratio of minus Rf by R. So we can also restrict the high frequency gain of differentiator circuit. Suppose if we connect a feedback capacitor in parallel with the feedback resistor Rf, we can further increase the stability and can avoid high frequency noise. So in this way we can construct a practical differentiator circuit to avoid limitations. Now if we observe this circuit, it contains two low pass filters, and because of these two low pass filters we have two cutoff frequencies as well. The cutoff frequency F1 because of input resistor and input capacitor, that equals to 1 divided by 2 pi RC. Another cutoff frequency F2 because of feedback resistor RF and feedback capacitor CF, that equals to 1 divided by 2 pi RF multiplied by CF. Let us assume that the cutoff frequency F2 is greater than F1. Now let us observe the frequency response of practical differentiator. So if the input signal frequency increases, the gain of the differentiator circuit will also increases at the rate of 20 dB per decade up to the first cutoff frequency F1. And if we further increase the input frequency, because of low pass filter action of the differentiator circuit, the gain will start to reduce at minus 20 dB per decade. So the plus 20 dB per decade and minus 20 dB per decade will cancel each other, and we will see a flat response up to the cutoff frequency F2. And if we further increase the input signal frequency, we will see the reduction of the gain at the rate of minus 20 dB per decade. So we can say that if the input signal frequency is less than cutoff frequency F1, the circuit acts like a differentiator. If the input signal frequency between F1 and F2, the circuit acts like a voltage follower or buffer. And if the input signal frequency is greater than the cutoff frequency F2, the circuit acts as an integrator. Suppose if both these input and feedback resistor and capacitor values are equal value, then both the cutoff frequencies F1 and F2 becomes equal. Let us say it is FA. We can write FA as 1 divided by 2 pi into RC. Now this differentiator circuit have only one cutoff frequency. In that case, if you see the frequency response up to the cutoff frequency FA, the gain will increase at a rate of 20 dB per decade. If we go beyond this cutoff frequency, then the gain will reduce at the rate of minus 20 dB per decade. So for proper differentiation, input signal frequency Fs must be between 0 dB frequency F0 and cutoff frequency Fa. So here also we can say that if the input signal frequency is less than cutoff frequency Fa, then this circuit acts as a differentiator. And if input signal frequency Fs is more than cutoff frequency Fa, the circuit acts as an integrator. We must choose the values of Cf and R by considering the requirements of noise compensation and bandwidth of differentiator circuit. The larger the values of Cf and R, they provide increased stability and noise reduction, but at the cost of bandwidth. The differentiator circuits are most commonly used in wave shaping circuits to detect high frequency components of input signal. Differentiator circuits are important part of analog computers and analog PID controllers. Differentiator circuits are also used in frequency modulators as rate of change of detectors. Now let's solve some examples on differentiator circuits. Find out the useful range for differentiation for the circuit shown in this figure. Here the values of input and feedback resistors and capacitor components are different. So we have two cutoff frequencies. Cutoff frequency F1 because of input resistor and capacitor, that equals to 1 divided by 2 pi RC. Let's insert the values of input components. That gives 15.9 kHz of cutoff frequency F1. Now the cutoff frequency F2 because of feedback resistor and capacitor. That equals to 1 upon 2 pi RF multiplied by CF. And that becomes 159 kilohertz. Here cutoff frequency F1 is less than cutoff frequency F2. So the input signal frequency must be lesser than 15.9 kilohertz for the differentiation of this circuit. Here also same differentiator circuit. But our input signal is a sine wave of 1 volt peak and 1 kilohertz frequency. We need to find out the output voltage. Because of the same circuit, here same cutoff frequencies F1 equal to 15.9 kilohertz and F2 equal to 159 kilohertz. So here our input signal frequency 1 kilohertz is much lesser than 15.9 kilohertz. So we can ensure that proper differentiation of input signal. Here we can write Vin as Vm multiplied by sine omega t. That equals to sine 2 pi 1000 t. Our formula Vout equals to minus Rf multiplied by C dVin divided by dt. Let's insert the values. If we simplify this equation, then our output voltage is 0.6286 multiplied by cos 2 pi 1000 t. So if you apply a sine wave input to the differentiator circuit, the output will be minus of cosine wave. So here the output signal amplitude depends upon the values of feedback resistor Rf and input capacitor C and also input signal frequency. If you change the values of these three parameters, based on that our output signal amplitude will also change. Suppose if we double the input signal frequency to 2 kHz, then our output will also get doubled. Here also same circuit. Now our input signal is a triangular wave with 10 volt peak to peak and 1 kHz frequency. Because of same circuit, our cutoff frequencies is also same. Here the input signal frequency of 1 kHz is much lower than cutoff frequency F1. So we can ensure that proper differentiation of the input signal. Here input frequency is 1 kHz. So the time period is 1 millisecond. In 0.5 milliseconds, our input signal slope changes from minus 5 volt to plus 5 volt. That is 10 volt. So the slope of this input signal is 10 volt divided by 0.5 milliseconds. That equals to 20,000 volts per second. Our formula for Vout equal to minus Rf multiplied by C dVin divided by dt. Here dVin by dt represents slope of input signals, that is 20,000 volts per second. Let's insert the values. Minus of 10 kilo ohm multiplied by 10 nanofarad multiplied by 20,000. That gives minus 2 volt. So our output voltage peak is 2 volt with inversion. So during the first half cycle or 0.5 milliseconds, the input signal slope is positive. So our output signal is minus 2 volt and the next input signal slope is negative. So our output signal reaches plus 2 volt in another 0.5 milliseconds. So in this way our output voltage will vary between minus 2 volt to plus 2 volt for the rest of positive and negative slopes of input signals. So in this way the triangular wave input will produce a square wave pulse. That's all about op-amp as differentiator. I hope in this video you have understand how to design a differentiator circuit using op-amp. So if you have learned from this video, please do mention them in the comment section below. Thanks for watching this video. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe my YouTube channel and turn on notifications for more such videos. My next video is op-amp as comparator. Have a nice day.